We began this chapter talking about phases, and now we're going to talk about phase changes. And there's a few important ideas here that will come back later, especially when we're talking about calorimetry. But the first thing to realize is that we need to be consistent in our terminology. So we can think about what the phases of water are, because water is a substance that we're most familiar with, and it's one of the few substances where we've actually seen it personally in all three phases. So solid water is just ice. Now be careful, because when you say water, you probably imagine a liquid, but when a scientist says water, they mean H2O, they mean a chemical compound. So to make it clear, when we mean liquid water, it's helpful to literally call it liquid water, because otherwise it's unclear if you mean liquid when you say water or you just mean in general the material. And the gaseous form of water is simply steam. So what a phase change then is when you're converting one to the other. And this is going to relate to temperature. So if I have a block of ice and I heat it, that ice is going to become water. If instead I started cooling it somehow, that water would start becoming ice. So how does this actually relate to temperature change? Something really interesting here happens. Imagine that I start with a big block of ice and I heat it. Now, I can heat it at a constant rate. We haven't actually talked about what heat is yet, so don't worry too much about that. But I'm basically putting a constant amount of energy in per unit time. Now, one thing to realize is that ice can be colder than 0 degrees Celsius, right? That's okay. So I can initially start with ice that is colder than freezing, and I heat it as I put in energy, it gets warmer. It doesn't immediately turn to water, right? Before ice can turn to water, it must get to 0 degrees Celsius. So initially the ice is warming up and then it gets to 0 degrees Celsius. It must all turn into water before it continues to heat up. Now, we are making the assumption that the entire thing is at one temperature for this to happen. So if you put a pot on the stove, the bottom would be a different temperature than, say, the top. So in our physics modeling, we're always going to assume, unless you're told otherwise, that the entire thing is at one temperature. During this flat period here, you have some solid, some ice, and some liquid water. That's okay. They can both exist at 0 degrees. As you put more and more energy in, you keep heating it, you're actually just converting that ice to water. Eventually, you only have water, and then the temperature starts increasing again. You then reach the temperature, 100 degrees, where the water boils. Now, it starts turning into steam. And again, at this point, you can have gaseous water and liquid water at the same time, but the temperature only starts increasing once it's all steam. And you can have steam that is hotter than 100 degrees. So keep in mind that just because you have ice or just because you have steam, that doesn't mean you have a fixed temperature. And one thing that we'll talk about later when we learn more about heat is what's going on in these periods of time where we know we're putting energy in, but we see the temperature not changing because the phase is changing. So another topic that we're not really going to come back to right now, so it's not that important, is that of phase diagrams. Where phase diagrams are important is that it actually tells us that there's a relationship between where these phase changes occur and pressure. So depending on where you've lived in your life, this might be something you know, because one of the interesting things about water is that where it boils actually changes depending on what pressure you're at. So typically we think about water boiling, liquid water boiling, at 100 degrees Celsius. But that's at kind of standard atmosphere of pressure. If we go to slightly lower pressure, as if we were up on a mountain somewhere, in this case, it's now converting between a liquid and a gas at a slightly lower temperature. So if you're, for instance, living on a mountain, you might actually use slightly different temperatures to cook food because this changes. This curve changes where you're going from a liquid to a gas. Now there's something called a triple point, which is one pressure and one temperature where you can actually have a solid, liquid, and gas of the same substance existing at the same time. So the triple point is actually a unique definer of temperature because you know that you have to adjust the pressure until you get it, and then you know exactly what temperature you have. So some substances in the book, it shows water and carbon dioxide, have this triple point. Some other substances actually have really complicated phase diagrams where maybe a triple point doesn't exist. But right now in intro physics, we're thinking about just 3 phases, not worrying about the crazy stuff that happens. And so we can think about substances having this triple point. And of course, for each different substance, you have a triple point occurring at a different temperature and a different pressure. So reading these phase diagrams are just helpful if you know a given pressure. You could then read off roughly what is the temperature that a specific process is happening. And again, where that happens at atmospheric pressure, just the air that we breathe around us when we're close to sea level, that is not necessarily the temperature that the same processes happen if you go to much higher pressures or much lower pressures.